Hello friends, in this video I will talk about basics of differentiation and integration and its practical examples. Differentiation and integration find applications in different scientific fields such as physics, chemistry, biology, engineering and economics. So let us start with differentiation. Differentiation is a process of finding derivative. To find derivative, we need to know what is a variable, an independent variable, and a dependent variable. So variable is any quantity, physical quantity, which varies. To understand dependent and independent variable, we take an example y equals to x square. Variation in x will lead to change in y. Therefore, x is an independent variable whereas y is a dependent variable. Generally, we call dependent variable as a function of x, that is f of x. Graphically, independent and dependent variables can be shown like this. X is independent variable, f of x is dependent variable. Once we know about the independent and dependent variable, we can define derivative. Derivative is the ratio of change in f of x with respect to small change in x. To find derivative, we need to know f of x, then f of x plus h, and take their difference. Then divide by the change in x. Change in x is h. Then make h as small as possible, close to 0. This defines the derivative of f of x with respect to x. Graphically, we show the derivative as shown in the figure. Change in x is h along the x-axis. See the dark blue line. Change in f of x or y is light blue line, vertical line. In fact, derivative represents slope as shown by the green line. Now we take a simple example to find the derivative of x square. F of x equals to x square. So to find the derivative, we need to know f of x plus h. And f of x plus h is x plus h raised to power 2. So using this formula, we get f prime x equals to limit h approaching to 0 and in this expression. So we now calculate x plus h raised to power 2, so which is easy to calculate. So finally, after doing some calculation of x plus h square, we get h plus 2x. So now take limit h approaching to 0 would give us f of prime x equals to 2x. Note that finding derivative this way is time consuming. There are well-defined formulae for various type of functions. For example, derivative of x raised to power n, derivative of x raised to power n is n into x raised to power n minus 1. So the derivative of f of x equals to x raised to power 2 would be 2 into x raised to power 2 minus 1, that is 2x. As I said, for various functions such as exponential, logarithmic, trigonometric functions, we have a well-defined derivatives as shown here. So we need to remember these formulae in order to use them. Now let us take a practical example to understand the use of derivative. The question is, what is the rate of change of volume of a spherical body at a radius of 5 cm? First, we need to know the relation of radius with the volume, and which we already know. The volume equals to 4 by 3 pi r cube. Here r is independent variable and b is dependent variable. Taking derivative of volume with respect to r will give us dB upon dr equals to 4 pi r square. Now this expression gives us a general variation of volume with respect to r for any value of r. So at r equals to 5 cm, we can just put r equals to 5 here, and then the answer would be 100 pi centimeters square. So far so good. Now coming to integration. What is integration? The synonym of integration is combining things. In a loose sense, it is basically summation. To understand the real meaning of integration, consider the following graph with x as independent variable and f of x as dependent variable. Here f of x equals to x square. Consider 2 points x equal to a and x equal to b on x-axis, then divide the distance between them into n intervals, each of size h. Then draw vertical lines at those interval points. Then look for values of f of x at x equal to a, x equal to b, and in between points. The values are at x equal to a, f of a, f of a plus 2h at x equal to a plus h, f of a plus 2h at x equals to a plus 2h, and so on. Now at x equal to a, draw a rectangle of width h and height f of a. Similarly, for x equal to a plus 2h, x equal to a plus 2h, x equals to a plus 3h, draw rectangles. Now note that the number of rectangles are equals to number of intervals, and number of intervals are n. Now we need to find area of all these rectangles. So as I said, the area of first rectangle is width of this rectangle and height of this rectangle, product of width and height, that is f of a into h. Similarly, the area of second rectangle is width is h and height is f of a plus h, so this one. And similarly, third rectangle, we have area, and in general for ith rectangle the area will be f of a plus I minus 1 into h multiplied by h. And for nth rectangle, the area will be f of a plus n minus 1 into h multiplied by h. Note that for third rectangle we have 2h, therefore for ith rectangle we will have I minus 1 into h. Now the approximate area under the curve is sum of all these rectangles, all these n rectangles. So if we know the area of ith rectangle, which is this one, then we take sum over all those n rectangles, and this expression can be written as sum of product of f of xi and delta xi equals to h. Since x square is a continuous function, so we need to take n approaching to infinity to approximate the area under the curve, and that's why we take limit n approaching to infinity. And basically this defines the integration of f of x, and this is integration symbol. So the conclusion is that the integration is sum of infinite area terms. Now let's take an example to make use of the integration. Question is, a car is moving with acceleration a equals to cos pi t along a path. At time t equals to 0, its velocity is 1/2 pi. So how much distance it travels in 1.5 seconds with respect to initial distance? So note that here acceleration is time dependent, and we know that the final velocity in relation to its initial velocity and acceleration is given by the formula v equals to u plus at. Here a is constant, but in our case a is varying with time. U is initial velocity and v is final velocity. So when the acceleration is varying with time, this formula cannot be used. We have to use the following formula. Here, for a small change in time dt, the acceleration would be a at, with integral of this term. So use this formula and we get v of t, velocity at time t, equals to initial velocity plus integration from 0 to time t of this term, acceleration is time dependent, multiplied by dt. So putting this term a equals to cos of pi t and taking initial velocity equals to 1/2 pi and the final time equals to 1.5 seconds, we can get the velocity vt equals to this expression. But again, the the question is how much distance. So we need to find the distance, and we are only finding here till this point the velocity, which is time dependent. So we need to further multiply this term by time so that the units are distance. So therefore we need to take one more integration of this term, and we use integration procedure on both side of this expression using this formula, and we get this term by putting v of t equals to ds upon dt and doing the integration. We will get this expression. So this is s is distance at final time 3 by 2. Basically it is difference of distance. S is 3 by 2 is 1.5 second minus s0 is initial time. So the distance traveled with respect to initial distance is this term. So if you put the value of pi, you will get this value to be 0.34 meter. Let's take another practical example of integration. A cone-shaped tank of water of height 10 meter with top radius of 2 meter is fully filled. So how much work is required to fully pump out the water from its top? The hint is we need to find the volume of water near arbitrary height of the tank, say h from the bottom, and then get the mass of that small region of the water, and then multiply by gravity will give us the work required to take out the volume of the water from that small region. And then we use the integration procedure to calculate the total work required to pump out whole water from the tank